I tell you, okay, roll this die and then draw a card for my deck of cards. Now that's two events. That becomes what's called a compound event. And the die has its own probabilities, and the deck of cards have their own probabilities. But if you're talking about rolling a 1 and drawing a 7, then you can actually calculate the probability of rolling a 1 and drawing a black 7, both at the same time. And that's a compound event. But it's made up of simpler events with simpler probabilities. The sample space simply consists of all the outcomes for all the events that can't be broken down any further. So in other words, going back to my example of a die, my sample space are the numbers 1, 2, 3, 4, 5, 6. It doesn't break down any more than that. If I toss a coin, I only have 2 possible outcomes. So my sample space is heads or tails. Now if I toss a coin 3 times, that becomes a compound event, and my sample space gets larger because I could get a head and 2 tails, or a tail and 2 heads, or all 3 tails, or all 3 heads, or any of a number of other outcomes. The notation that we're going to use here is going to be that capital P represents probability. And whatever comes in parentheses after capital P is some way of explaining what the event is. We don't want to have to keep writing out the probability of rolling a 2 on a fair die is. So what we'll do is we'll just denote that event A is rolling a fair die. And here's our first example. If you flip a coin, what's the probability that it'll land on heads? Now everybody in here ought to be able to answer the question without looking at the notation. If I flip a fair coin, what's the probability my coin lands on heads? 1/2? 50%? 0.5? All those are good answers. Probabilities are numbers between 0 and 1. 0 means it can't happen. 1 means it has to happen. If I flip a 2-headed coin, what's the probability I flip a head? 100%. 1. Because it's got 2 sides, but both of them have a head. Okay? So if you flip a coin, what's the probability it'll land on heads? You say that event H is the coin lands on heads. And then you write P parentheses H, and you say P of H, or the probability of H is. And in this case, the rest of that would be probability of H is 1/2, or the probability of H is 0.5, or the probability of H is 50%. Okay? We're going to have to talk about something called the fundamental counting principle, and I've actually posted a video, a correct video now. It was chapter 3, now it's chapter 4. I've posted a video that explains the fundamental counting principle and some of these other things so that you'll have it to refer to. If an event can occur in M ways, and a different event can occur in N ways, the number of ways they occur together is M times N. That's nice. What does that mean in English? Okay? That's what I'd be thinking. What does that mean in English? I don't count in M's and N's. Whoops. Back up. So this is an example of fundamental counting principle.
Let's try a few examples using the fundamental counting principle. Example number 1. An apartment complex offers apartments with 4 different options designated by A through D. Option A is the total number of bedrooms. You can have 1 bedroom, 2 bedrooms, or 3 bedrooms. We've got 3 choices here. Option B is the number of bathrooms. You can have 1 bathroom or 2 bathrooms. We have 2 options here. It could either be on the first floor or the second floor of the apartment complex. There are 2 options. You can have a lake view apartment, a golf course view apartment, or no special view at all. And so there's 3 choices. According to the fundamental counting principle, apartment options are available. We will find this by saying 3 times 2 times 2 times 3. All right, so I've got 3 times 2 is 6 times 2 times 3. And then 6 times 2 is 12 times 3 is 36. There are 36 different options available. One of those options would be a 1-bedroom, 1-bath, first floor Lakeview apartment. Or I could have a 1-bedroom, 1-bath, second floor Lakeview apartment. There are a total of 36 different ways that I can combine my options. All right, let's try another example. Okay, example number 2. A car model comes in 9 colors, with or without air conditioning, with or without sunroof, with or without automatic transmission, and with or without anti-lock brakes. And how many ways can a car be ordered with regard to these options? All right, so as far as colors, we have 9 colors. We have 2 choices for AC, either with or without. We have 2 choices for sunroof, either with or without. And we have 2 choices of transmission, either automatic or not. And we have 2 choices for the types of brakes, either anti-lock or non-anti-lock. In order to find the total number of ways that this car can be ordered as far as the options are concerned, we will multiply 9 times 2 times 2 times 2 times 2. Now, according to the order of operations, I can just work left to right. 18 times 2 times 2 times 2, 36 times 2 times 2, 72 times 2 is 144. So there are 144 different ways to order this car with the options that are available. Now, if you look at your patterns here, from experience that you've had in previous courses, you could write this as 9 times 2 to the 4th power. Exponents could occur first then. That would give me 9 times 16. And then 9 times 16, that's 54. 91 plus the 5 is 144. All right, let's try another example. How many different 4-letter radio station four-letter radio station call letters can be formed if the first letter must be a W or a K? All right, so we've got 4 letters that we're going to choose. The first letter has to be a W or a K, so that gives us 2 options. The second letter can be anything A through Z. That's 26 options. The third letter can be anything A through Z, so there's 26 options. And the fourth letter can be anything A through Z, so we have another 26 options. All right, so we're going to multiply our choices here. This one's getting a little big to do by hand. Let's pull up a calculator. This is just the calculator available in my accessories on my computer. You have the option there when you're viewing the calculator to either view a standard calculator or scientific. I just have this one on scientific. All right, so I've got 2 times 26 times 26 times 26 equals. That's going to give me 35,152 different call letters that radio stations could use if the first 2 letters have to be a W or K. Now, I could have put this in my calculator as 2 times 26 to the 3rd power. The nice thing about a scientific calculator is that it does perform according to the order of operations. So I've got 2 times 26 to the, notice this key right here, X to the Y, so to the,
I think we already know how to do that. Okay?
And we're going to talk here about something called a tree diagram. Maybe. Yeah, maybe not. Maybe I'll talk about a tree diagram. It's taking my clip too long. Let me demonstrate a tree diagram before you do this. Let's talk about those apartments. So I'll grab a sheet of paper if you want to follow along on this. Remember the apartments that we were talking about? You could choose 1 or 2 bedrooms. Good grief, it's terrible. Have you decided to be still now? Okay. So 1 or 2 bedrooms. One or 2 bathrooms. First or second floor. And then we had what we wanted to view. Okay, so that was no special view. So the way a tree diagram works is you take your first choice, and that's how many bedrooms do you want? And your choice for bedrooms is 1 or 2. Now, if you chose a 1 bedroom, you could also choose a 1 bath. Or you could choose 2 bathrooms. Same thing if you chose 2 bedrooms. You could choose 2 bedrooms and 1 bath, or 2 bedrooms and 2 bathrooms. Then you can choose first floor or second floor. So this is a 1 bedroom, 1 bathroom, first floor apartment. 1 bedroom, 1 bathroom, second floor apartment. 1 bedroom, 2 bathrooms, first floor. 1 bedroom, 2 bathrooms, second floor. 2 bedrooms, 1 bathroom, first floor. 2 bedrooms, 1 bathroom, second floor. 2 bedrooms, 2 bathrooms, first floor. 2 bedrooms, 2 bathrooms, second floor. And then off of each one of these, we've got 3 different options for the view out of our apartment window. 1 bedroom, 1 bathroom, first floor, lake view. 1 bedroom, 1 bathroom, first floor, golf course view. 1 bedroom, 1 bathroom, first floor, facing the alley, or whatever, facing into your neighbor's living room. And the same thing, if you chose 1 bedroom, 1 bathroom, second floor, you could have a lake view, golf course view, or nothing special. Or if you choose 1 bedroom, 2 bathrooms, first floor, lake, golf course, no special view. And you're gonna have those same options coming off of all of these. So this would be a 2-bedroom, 2-bathroom, first floor apartment with a lake view, or a 2-bedroom, 2-bathroom, first floor with a golf course view, or 2-bedroom, 2-bathroom, first floor apartment with no special view. Or you can swap out your 1-bathroom for 2 baths and have the same options. So that's why the fundamental counting principle actually comes out the way that it does. If we actually filled out all of these, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 different options. Okay? The difference in this and just counting them, I mean, I wouldn't want to draw this if I was just trying to figure out how many. If I was trying to figure out how many, I would want to go 2 times 2 times 2 times 3. Okay? But if I actually needed to list out all the options for whatever reason, then I might want to do this, because I could follow any line all the way out to its end to describe the whole apartment. Now this one's actually a fairly complicated diagram to draw. So let's try one that's a little bit simpler. Let's suppose that we're going to roll a die and then flip a coin. And we want to list out all the ways that that can happen. When you roll a die, how many things are there that can happen? What are your outcomes? 1 through 6. So you can roll 1, 2, 3, 4, 5, or a 6. Now if I roll a 1, what happens next? I'm going to flip the coin. What could I get? Heads or tails? What if I rolled a 2? What if I roll a 3? And the same thing with 4. And 5 and 6. So one of my outcomes would be that I would roll a 1, then a head. Or I could roll a 1, then a tail. And an easier way to write that would be using my sample space notation, 1 comma H and 1 comma T. That's the way you would actually want to write your outcome so that you could tell what was happening when. So then this would be 2, then a head, 2, then a tail. This would be 3, then a head, 3, then a tail. 4, then a head, 4, and then a tail. 5 and a head, or 5 and a tail, or 6 and a head, or 6 and a tail. And I could use this to actually figure out the probability for any of these events, because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And as long as my coin's fair and my die's fair, those 12 different possible outcomes occur about 1/12 of the time. Each one has the same probability. Now, if I were to ask you, what's the probability you roll an even number and then a head? Well, that would be this one, and this one. So then that answer would be 3 out of 12. What's the probability of an even number and then a head? And that happens 1, 2, 3 different ways. So that will be 3 out of 12, which is the same as 1/4, which is the same as 0.25, which is the same as 25%, and all of those answers are perfectly good. Now in the My Math Lab, they're going to make you reduce your fractions. 3/12, 1/4. Use your calculator. Does anybody not know how to use your calculator to reduce a fraction? Because we can look at that. Okay. Let's use a calculator to show how to do that. Let me go find my calculator. Okay, if I've got the calculator and I want to change 3/12 to a completely reduced fraction, I say 3 divided by 12. And then I go to my math key. And the very first thing at the very top is frac, for fraction. So I hit enter, and then I hit enter again, and it changes 3/12 into 1/4, which is completely reduced. Okay? So that's how you do it. Now, if you wanted to change it to a decimal, you just do the same thing. But you don't put the frac after, and it gives you 0.25. And then the way you change from a decimal into percent, you move your decimal twice to the right, and you add a percent sign. That part you should have had practice with in the 0530, but if you're still kind of shaky on that, that's how you do that. Does anybody have any questions so far? Okay, let's go back to the Nearpod lesson for just a minute. You flip a coin, and then you roll a die. Draw the key of the tree diagram and show all the different possible outcomes. How many possible outcomes can occur? Now it's very similar to what I just did with you, but notice what comes first. When I did it, I flipped the coin after I rolled the die. You're going to flip the coin and then roll the die. So you're doing it in the opposite order. Draw me the tree diagram. If you're on the computer, you can draw with your mouse. And right now, I'm hiding everybody's name because I just want to see if you got it. I don't care if everybody sees everybody else's drawing. I just don't want you to know whose drawing you're looking at. I know it is. This is called a amusement break. It doesn't have to be perfect. We get to laugh at each other. Read what it says first. Okay, you flip a coin, and then you roll a die. So how many outcomes on the coin? Okay, and then after that you roll the die. ain't trying to put it all on a sheet of paper up there. That's all you have to do.
Is it a
Oh, you
six-
have to answer the question, how many ways can it
Is
occur?
it a 6-number, die?
It's a 6-number die.
So.
Yeah, my son's a gamer, I'm aware there are other than 6-sided die. I'll show you something that might make it. Go here.
Oh, you know what, I should make this a heavy over space.
It's easier for you.
Where's my eraser?
One of the things that I'll have to show you individually, you can, at the bottom, when it pops up the pins and the eraser and stuff, you can influence how big your line is. You can actually, there's a little slider to make your line thicker or thinner.
I didn't change my mind after that. Or no, yeah. Okay, so how do I get back?
Yeah, you can make it thinner than that if you want. Just move the slider down, see what happens. Okay? Yeah, they've improved this a lot since I started using it. But I like to do this because, you know, sometimes it's kind of fun to see everybody else struggle drawing in a mouse. Nobody can laugh at you because they're not doing any better than you. Okay, now anybody that's thinking, I just can't do this, look up here, everybody else is doing.
Oh, my.
Oh, my gosh.
Sometimes you just need to laugh.
I didn't even.
Now, we are gonna do this some more, there's a lot, when we come, you know, those of you that are in chapter 6, you see those little curves, those bell curves? We're gonna draw bell curves on these things too. You're gonna get better at it.
What do you get tails?
Hmm?
Okay.
Okay. Yeah, but you can't get tails and tails, because you're only gonna flip it once. Okay?
Would it go?
See, y'all aren't doing so bad.
This thing is.
I don't know whose this is, but you need to revise your tree diagram. You might want to check out your classmates' work there. Because you don't make two separate ones. The first one is, what did you do first? You flipped the coin. What happens? Two things. Then, from those two things, you roll the die. So there should be 6 lines coming off each of those two things. And those of you that are sitting there still struggling, stop trying to be a perfectionist. Okay. Everybody needs to turn it in. 3 more. You want your participation point for today, draw your diagram and submit it.
Hey, can you give me a participation point, looking at it on this paper? So I didn't hurt you.
No, you gotta do it with everybody else.
That's what it says.
I don't, I thought we did all of it. I really have to do one.
The whole review reaction. For participation in class side. This may not have any sound with it when y'all get it, I don't know. Okay, it came back up. It acts like it turned the microphone off. Okay. Looks like I'm still waiting for one. Zach, if that's you, we'll give you a pass this time. Okay. I'm actually going to move out of this now. We'll come back to it at another time, but I like to do something that's a little bit more fun now. So here's what I want you to do. I want you to get your pumpkin handout. Let me pull up my pumpkin handout. Back here. Okay, there's our pumpkins. And I printed one off for me so that I can read the questions without having to move the pumpkins. Probability is the number of ways that something you're counting happens compared to the number of ways total it can happen. Your desired outcome is not going to necessarily be all of the outcomes. For example, if you're going to buy a lottery ticket, what are you hoping your lottery ticket has on it? Winning number, right? But how many tickets got sold? A lot. Have you been guaranteed all those tickets have a winning number on them, or any of them have a winning number on them? No. In fact, we're going to do a little project later on to talk about playing Powerball. You're going to realize how hard it was to get that winning ticket for that $5 million. Or what was it, $5 million or $15 million? It was a bunch. Okay. What we have here are pictures of pumpkins. Duh, it's Halloween. You're supposed to have pumpkins. Okay, some of the pumpkins have stems and some of them have hats. Some of them have a face carved on them and some don't. Some of them have noses and some don't. We're going to answer the questions. Find the probability of choosing a pumpkin that's carved. When we're finding pumpkins that are carved, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 carved pumpkins. Okay? 20. But how many pumpkins are there total? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, and 3 rows of 8 is 24 pumpkins. And how many of them are carved? 20. So 20 over 24 is? If we want to change that to a decimal or percent, we do that on the calculator. So it's 5/6. Or 83.3%. Okay? Second one says find the probability of choosing a pumpkin that has triangular eyes given that it's carved. Triangular eyes given that it's carved. Now I'm going to ask you a question about that. Can it have triangular eyes if it's not carved? No, so does it, given that it's carved, really matter? No. So how many have triangular eyes? 15? So it's 15 over what? 15 over 24? What does given that mean to you?
The only ones you're looking
That should be the only ones you're looking at. It's saying you're only, it's saying basically when it says given that it's carved, it's saying only look at the carved pumpkins. Now I realize that most of us are sitting there saying, well, duh, that's, you know, it's not gonna have eyes if it's not carved, but they're only counting the ones out of the carved pumpkins. So maybe the question they're trying to answer is what percentage of the pumpkins that are carved have triangular eyes. So you have to actually pay attention to that, given that. That given that is a very, very important phrase in probability. It means it's guaranteed and you only count those. Yes?
The fraction you have, 5/6, how do you get that when you can't divide 15 or 40?
Oh, that's not right. I just copied and pasted. Okay? So how many carved pumpkins do we have? Because 24 is all of them. Not all of them were carved. How many are carved? 20. So that would be 3/4. Now y'all can do the fraction changes. I've showed you how to do that. And then that would be 0.75. And that would be 75%. And in this case, it's okay to put 75% because it is actually 75%, not 75 point anything else percent. I will warn you though, if my math lab says round your decimals to one, or round your percentages to one decimal place, it would want that answer to be 75.0% to show that you knew it wasn't 75.1%. Okay? So just watch my math lab. It can be very picky. Next one says, find the probability of choosing a pumpkin that's wearing a hat. How many hats do we have on pumpkins? 4 hats? And that's out of all the pumpkins, right? So that's 1/6. And I think that's right. Yep, I can still do fractions. So that'd be 16.7%. Find the probability of choosing a pumpkin with a hat given that it's carved. Now that's 4 out of 20 because we're only looking at the carved pumpkins. And 4 out of 20 is 1 out of 5, which is 20% for 0.20 or 0.2. Find the probability of choosing a pumpkin that doesn't have a nose given that it's carved. How many of our carved pumpkins don't have a nose? 1, 2, 3, 4. So again, it's the same thing. If you select 2 pumpkins at random, without replacement, which means we're not going to pick one, look at it, and then put it back. We're going to pick one and say, this is what I got, and put it on the table and not put it back with the others. Find the probability both of the pumpkins you pick have hats. What's the probability the first one you choose has a hat? Okay, because we already figured out the hat, that's 1/6. Now, what are we going to do with that pumpkin? Or, because the probability we got one is 1/6, are we going to put it back? How many pumpkins are still in the patch now? Twenty-two? 23, okay. There's 23 pumpkins still there. How many of the ones that are left have hats? Yeah, only 3 of them, because we got one sitting on the table in front of us. Now, I usually get a question about that. It's gonna be 3 over 23 for the second one. So I have the probability of getting the first one, that's actually 4 out of 24, which is 1/6. And the probability of getting the second one, which is 3 out of 23. And at this point, we're gonna have to talk about, there's gotta be some kind of a rule that tells us, you know, how many ways there are to pick those pumpkins. Now, there is a shortcut rule. The long, hard rule would be to go up there and take every single pumpkin and list every single mate it could have. That would take a while. We don't want to make tree diagrams. So I'm going to tell you what the rule is. And I really can't spell. And means to multiply. And your question is, okay, multiply what? Multiply the 2 answers you got so far. And for that, you want a calculator. And the way you would write this is the probability that you get the first one with a hat and the probability you get the second one with a hat together. And that word "and," how are you going to have both of them have a hat if the word that goes there is an "and"? What if you didn't draw a pumpkin with a hat on the first draw? Are both of them going to have hats? No. So we have to assume that the first one had a hat in order to even have a chance at both of them having hats. Because if the first one doesn't have a hat, then, you know, we may as well just quit playing. The second thing's not going to happen. So we're only interested in outcomes where the first one has a hat and the second one has a hat. And the word "and" is going to tell us to multiply our options.
So in this question, we're trying to develop a probability for a positive outcome, basically.
Yes. Yes, we're developing, and that's what the basic of this probability is. The positive outcome is you get what you want.
So we're not looking for the variable of if it never happens.
Yeah, if it never happens, no, that's, yeah. We could actually find the probability that neither one of them have a hat, because we would do the probability that the first one doesn't have a hat times the probability that the second one doesn't have a hat. Okay? You just have to be careful how you word it, and that's one thing I want everybody to pay attention to. Wording in probability questions can be confusing. If you don't think you understand what's being asked in the probability question, ask for clarification. The probability of the first one having a hat and the second one having a hat is not necessarily the same thing as the probability of the first one having a hat and then the second one having a hat. Sometimes that word "and then" makes a difference in whether or not the second thing can even happen. Okay? Nick, I think you had a question.
I was gonna see if you could scroll it up. I think-
Oh, okay. Yes, I can definitely scroll it up. So 1/6 times 3/23, again, I'm gonna use the calculator, I don't expect you to do otherwise, but I am going to warn you, you need parentheses. You do not type in 1 divide 6 times 3 divide 23, because you will not get the right answer. You need the parentheses. And if I try to do that as a fraction, it's probably going to tell me there's not a simplified one. Well, actually there is, sort of. So it's 1/46. But, you know, I don't really, in my brain, 1/46 doesn't really give me a numerical sense of what that means. So I kind of like the 0.0217. Because the 0.0217 says there's about a 2.2% chance of drawing 2 pumpkins with hats out of that pumpkin field. And I realize, hey, 2.2% is not very likely to happen. I don't want to bet on that. Okay? So there's the other ways you can write your answer, but my preferred way would actually be that percentage. Find the probability of choosing a pumpkin that's carved and has a zigzag mouth. I count 9. Y'all agree? And of course, if it's got a zigzag mouth, it has to be carved. So did it say given that it's carved? Or did it say just and it's carved? And. So how many pumpkins am I counting it out of? Only the carved ones or all of them? I think I'm counting them all. Okay? What did I tell you and means? And means multiply. So I need actually to find the probability that it's a carved pumpkin. What's the probability of a carved pumpkin? Okay. And the other one is zigzag mouth. And there were 9 of those out of all of the pumpkins, and all of the pumpkins was 24 pumpkins, right? Get my divided by in there. And remembering that and means multiply, because there's that word and, then what we're going to multiply is
9/24
Shouldn't be 9 out of 23 since we've already picked one out of the 24.
we're only choosing one pumpkin.
No. that's right.
Okay, we're only picking one pumpkin, but that's a good thought. So probability carved and zigzagged. Yes, you can reduce that, Zach, you could. But since I'm gonna multiply it out with something else anyway, then I don't think I'm gonna bother. What I'm gonna do is I'm just gonna put in the fractions I've got. And get a totally reduced answer, which is 5/16. And there again, I think I would rather know what that is as a decimal or percent. What about you? Because I can interpret percentages a lot better than I can fractions. So 5/16 is 0.3125 or 31 point, we'll call that 31.25%. Okay? Number 8 says find the probability of choosing a pumpkin that has a nose, given that it's carved. Which pumpkins are we looking at? All of them? Only the carved ones, and there are only 20, okay? So how many of the 20 have noses? 16 of them? And 16 out of 20 is 8 out of 10 or 4 out of 5, which is equal to 80%. I'll let y'all verify that for yourselves. Find the probability of choosing a pumpkin that has triangular eyes or a nose. Now we're going to have to count carefully. We're talking about out of all the pumpkins, so it's going to be out of 24 pumpkins. Question is how many? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I agree with that answer. There's 20.
You have to count both the triangular eyes and nose with that answer.
Well, that was what I was about to talk about, so I'm glad you asked that. Let's go back up here and count. Now we're looking at the ones that have triangular eyes. Now, be careful and watch how I'm counting this time. Triangular eyes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 that have triangular eyes. Okay? Now I'm going to count noses. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 noses. Add those two together. What do you get?
30.
So how come the probability is not whatever that is out of 24?
Because it's combining, it's not like, it just said eyes and then noses, so it didn't combine the two like it normally would. I know I worded that really wrong.
Yeah, but I understand what you're getting at. Let's go back and look at the way it's worded. It has triangular eyes or a nose. Now my brain tells me when I count that, oh, well, that's easy. Go count all the ones that have triangular eyes, and then count all the ones that have noses, and then add those together.
Yeah.
But what's the problem with doing that?
Then you're calculating
Doesn't
something
mean
that has
either.
both.
Hmm?
Then you're calculating something that has both instead of either or.
No, they have or, it's either or, but here's the problem. If I count this one as having triangular eyes, and then I count him again as having a nose, he was counted twice. So was this one, so was that one, and that one, and that one, and that one, and this 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 one. I counted a bunch of them twice. And the answer doesn't even make any sense, because if I count all the ones that have triangular eyes and add that to all the ones that I counted separately that had noses, I get more pumpkins than what I had the whole patch. Right? And that's not possible. So you've got to think logically here. Now there is a rule that's going to come up in probability. We will talk about it, but I want you to remember this conversation when we get to that rule, because it's called, there's an or rule and an and rule. Now, I just told you what the and rule was because it's easier than trying to make you figure out what it is. But the or rule, you have to be very careful when you're doing or. If you've got a situation where you're just given the words and not given the picture, you have to think back to, when I double counted this, I got an answer that didn't make any sense. So you have to consider what you're going to do not to double count. Okay? If I've got pictures, it's easy, because I'm only going to count these one time if they have either the eyes or the nose or both. Because if they have both, they've got eyes or nose. Okay? And then the last one says, find the probability of choosing a pumpkin that has a zigzag mouth. And what's the given condition? Has to have a nose. How many pumpkins have noses? 16? And in probability notation, the way you would write that, and that part's lazy. Probability of a zigzag mouth, and then you use the words given that, get a horizontal line. A vertical line, thank you. My arithmetic and geometry brain are not working right now. So given that, it has a nose. That's the short way of not having to write it all out. So we know, see how many we got with noses? You said 6, 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I missed somebody. I'll take y'all's word for it. So how many of those had zigzag mouths? Let's see, that one's got a zigzag mouth but no nose. Okay, there's 1, 2, 3, 4, 5, right? 5 of them. So 5 out of 16. I think we already did that for a decimal, so let me see if I can find where I did it. Maybe not. So that would again be 31.25%. Okay? Now, does this worksheet make sense to you? If I were to give you one like this to do for homework, could you do it?
Wouldn't want to, but could do.
Wouldn't want to, but you could? Well, actually, I am going to give you one for homework. And I will put up notes that goes along with the video, not this one, but the other little short video that's up there, the one that has the pink background on the PowerPoint. So I'll put those 2 things up, and I will see you on Wednesday.
Do we have to take a picture of this and upload it? Okay.
No, this was in class. You did not have to submit it for a grade. Okay, but there will be something in that same folder that you will need to do in Shovie and submit for a grade. Plus the notes will be up there, and I'll put the notes up there both as a Word document and as a PDF, so you can use whichever you want. See you Wednesday.